broadly different kinds of machine learning that are used in practice in artificial intelligence. Historically, there have been several approaches in machine learning for artificial intelligence, supervised learning, unsupervised learning, reinforcement learning, case-based reasoning, inductive logic programming, explanation-based generalization, etc., etc. There have been several examples of waves of machine learning for different AI problems. But of them, the three most important categories of machine learning which are of practical use for business use today happen to be the three of the below. Supervised learning, unsupervised learning, and reinforcement learning. Let's look at each of them separately, and we'll have a brief summary of each of them so that we have an idea of what we're talking about. Supervised is today the most mature and probably in some sense the easiest form of machine learning. The idea here is that you have historical data with some notion of output variable. When you say output variable, basically it is meant for identifying how you can get a good combination of several input variables and corresponding output values as historical data presented to you. And then based on that, you try to come up with a function which is able to predict an output given a new input. So the key idea here is that the historical data is labeled. Labeled, that means you have a specific output value for every row of data that is presented to it. So in that sense, the problem of supervised learning is that you really can only work when you have clearly labeled data with input-output values for all the historical data that is present to you. Then once you have the historical data, which is in form of several input variables with their values and corresponding output value present with you, you can use that to kind of infer a potential function between the input and the output. And that function can be actually used for any new input that is coming in and to guess the corresponding output. Whether the output is discrete or continuous, it does not matter, both are supervised learning. Specifically in the context of output variable, if the output variable is discrete, it is called classification, and if it is continuous, it's called regression. So in case of classification, the formula of a function takes a new input and potentially classifies them into one of the discrete possible output values. Or in case of continuous, you take the input values and give a corresponding continuous value to the output. So an example in discrete, it could be like a spam classifier, which takes input data and converts that into either spam or non-spam. Or a continuous data could be stock prediction, where you look at a lot of data from history of potential stock prices in different conditions and predict the exact value, and you get the output function and then use it for a potentially new scenario where at a new instant with different conditions of environment, stock price is calculated. So what happens in supervised is you have the luxury of having labeled historical input-output data. Then comes the unsupervised learning. Unsupervised learning does not have the luxury of having labeled historical data, input, output, combinations, etc. Instead, you can only say it has whole bunch of input data, raw input data. So what does unsupervised learning give you? It allows us to identify what is known as patterns in the historical input data and allows us to identify interesting insights from the overall perspective of a interesting pattern or insight on the original input data. So there is no explicit equation or a pattern which reflects a relationship between input or an output. So the output here is absent, and all you need to understand is there some pattern being visible in the unsupervised set of input. Example is, suppose you look at identifying in a large supermarket transaction set which two items are often bought together. There is no output here. Only we are talking about what are the collection of items which are frequently bought together. So that's like extraction of common occurrence kind of collection of items together. So that does not need labeling. It only has explicit no input, no outputs, but only explicit inputs. All inputs are then run through an algorithm and pattern extracted. The beauty of unsupervised learning is that it lends itself to numerous combinations of patterns, and the problem is because of its diverse nature, there is no one notion of unsupervised. Okay? One pattern means one context something, in another context of data it could mean another pattern. So there is no standardized notion of what is a good unsupervised algorithm. That's why unsupervised algorithms are harder, problems are tougher and more difficult to deal with. Next comes reinforcement learning. Reinforcement learning is basically a goal-directed learning approach where typically you are required to reach some goal state, and it is possible that you have to traverse a whole set of steps as you go along from the start position to the goal, which is the end position, and there are several steps in between, and at each step you can take multiple actions. So what happens is there is some notion of a start function, start state, there is some notion of a goal state, and then there are multiple states in the middle. And at each state, you can take multiple actions. Multiple actions possible at each stage, and each action has corresponding reward or a punishment. So what happens with this notion is, because you're talking about a collection of states, one is start state, one is end state, there are multiple goal states, not one. Then each state having corresponding mapping to an action to corresponding rewards and punishments. So ultimately what reinforcement learning does is it allows a machine or an agent to take steps and go from one state to another and takes action at each step, and which takes it to another state and action at next step. But as we keep going along, it collects the output based on experience, whether it is positive or negative, is it rewarded or punished. Based on that, it optimizes the steps taken and the path taken, and it incrementally increases its knowledge of which is probably a better path in terms of better rewarding, in terms of reaching goal faster or finishing a task faster. So in that sense, reinforcement learning is dynamic, state dependent, and constantly it keeps updating rewards and punishments also as it keeps learning from experience. So in that sense, history may not be there at the start, but history builds as it goes through actions, states, rewards, punishments at each step. So for example, in a classic example of a maze learning, where a starting agent starts from start point to end, if it hits an obstacle, it treats that as a punishment and it gives negativity to it itself. And in the future, it remembers and tries to go to paths which do not lead to potentially a blockade. So what happens is you're trying to reach the goal faster by remembering more and more of the moves which do not lead you to the goal, instead take you to a hindrance, and that knowledge is built accumulatively. And reinforcement learning dynamically continues updates the rewards and punishment knowledge, and builds a system is able to learn from experience and do an optimal reaching the goal. So these three broad categories form the basis of modern AI systems, where machine learning is entrenched into AI systems.